In this video, we will remember the concept of system, how it interacts with its environment. We will talk about the first law, its details, and we will learn about fundamental and characterizing dependent variables. Let's start with the system potato. As we have seen already, our system interacts with its environment through heat exchange, through work exchange, and through mass exchange. The heat exchange occurs across a diathermal wall. The absence of a diathermal wall makes the system adiabatic. The mathematical description is heat term is equal to 0. If our system doesn't exchange mass with its environment, we call it closed. Otherwise, it is open. And if the system doesn't exchange neither heat nor mass, the system is called isolated. Now, we have already derived the first law. I will write the first law as we have derived it over here as the time rate of change of total energy within the system boundaries is equal to the rate of energy exchange with the environment through mass exchange that comes in minus the energy exchange due to the mass flow out of the system boundaries. Let's get a clean erase. Yes. EI m dot I. And the reason that we are writing in a summation term is to indicate that this energy exchange is due to multiple streams that are coming in and multiple streams that are going out of the system, plus the heat term, plus the shaft work term, minus P dV over dt term. This is surface boundary movement term, and I'm going to write just underneath two more terms, and they were the PV terms. PV work, P times V of stream I multiplied by its mass minus outgoing stream of P times V I times m dot I. And these two terms are flow work terms. Now let's remember why we have dots. The dots indicate, the dots on top indicate that this is mass flow per mass, kilograms per hour, for example. So if I don't have a dot on the energy term, it is just simply has the energy units such as kilojoules. All right, when I write an equal sign in brackets, it means that it has the units of. And of course, if I have Q dot to be equal to 0, this has the units of power or kilojoules per hour, for example, that our chosen time has the units of hour. So this is the first law as we will start using. This is the system potato that we will use to understand realistic problems. And let's start to expand the energy term. So I'm going to do it on this side. Energy is the sum of the kinetic energy, of the potential energy, of the internal energy, and perhaps nuclear energy, perhaps electromagnetic energy, and so on and so forth. Now, we will have situations that we have to worry about kinetic energy and potential energy, but most of the problems that we will be dealing with in this course will focus mostly on what we call the internal energy. So I'm going to simplify the equation, leaving out kinetic energy, potential energy, nuclear energy, and electromagnetic energy terms, and focusing only on the internal energy. And then I will define what I understand from the internal energy. Then we will move on to the concept of fundamental and characterizing dependent variables. Okay, so if I simplify energy in terms of internal energy, what I mean is that the other forms of energy may exist, but they are not relevant in the time frame of our interest or in the system boundaries that we are interested in. So I will just I wrote the approximate equal, that energy is approximately equal to the internal energy. Then I will write my balance equation, energy balance, as d du over dt, y E is approximately equal to U, to be equal to summation of all the streams that come through the system boundaries, incoming streams. I will combine m dot I, these two terms, ui plus pi vi with a hat. And the hat means that it is per unit mass. I will come back. Minus summation of all the streams that are going out, m dot I, ui plus pi vi. All right, plus q dot plus shaft work minus p dv over dt. Now this u with no hat, no dot, is the total energy of the system. Okay. Whatever is in the system potato, it is U. Total energy of the system. This UI, say it is U hat 1, is the specific internal energy of stream I. Say that I have 3 streams coming into this system. In specific internal energy, meaning that energy per unit mass of stream 1, energy per unit mass of stream 2, energy per unit mass of stream 3. This is the pressure of that stream. This is the specific volume of that stream. So we specify each stream in its own state and obtain values for internal energy, pressure, specific volume. They bring in this amount of energy, they take out that amount of energy, plus heat, plus shaft work, minus the surface boundary moment. Now this term has a new name. We call it enthalpy. H is U plus PV. For this session, we will just say that this is just a matter of convenience, that instead of writing 3 different letters, we are writing one single letter, and we represent the whole thing in one single word. So now my energy balance simplifies. du over dt, that is equal to sigma of all the streams that are coming in, m dot I times hi, specific enthalpy with a hat, minus of all the streams that are going out, m dot I hi, plus the heat exchange of the system with its surroundings, plus shaft work minus P dV over dt. So once we know why we have each of these terms, where they came from, it will be very easy to analyze a problem and generate a solution for the problem. Of course, this balance equation has a coupling mass balance, dm over dt, to be equal to summation of all the streams that are coming in with mass flow rates that are defined by the system parameters or by the nature. So conservation of mass, conservation of energy, system and its environment, our state variables, our intensive and extensive variables. Now we are ready to solve engineering problems.